Hello, welcome back to Physics 211. So far in this course, we have been looking at electricity, and we've looked at electric charges. We saw that they could be either positive or negative, and that those charges create electric fields. Now we will start looking at magnetism. Magnets have both a north and a south pole. All magnets have both a north and a south pole, and those magnets create magnetic fields. The image that you see in front of you is that of the aurora borealis, also known as the northern lights. We see this because of Earth's magnetic field that is protecting us from the solar wind, which is radiation that if we were not protected from this by Earth's magnetic field, it would cause damage to all life on Earth. So let's start to understand magnetism by doing a few experiments. The first experiment that we're going to look at is we're going to tape a bar magnet to a piece of foam and allow it to float in a dish of water. So we're going to tape our bar magnet here to a piece of foam so it can move, so it can rotate in any direction. And when we put it in the water, we're going to see what happens. And down here for reference, we have a compass that is showing us which direction is north and which direction is south. So let's watch for a second what happens in this once we have our experiment start here. So when I put the magnet in the water, I intentionally had it misaligned with Earth's magnetic, I had a compass there so I could see which way Earth's magnetic field was aligned and which way was indeed magnetic north. And that way it allowed the magnet to then line up with with what is north and south due to the compass, just as it is here in this picture. And so we see that the magnet started to rotate to a line. It overshot because it had inertia, and then it came back until it actually stopped when it was pretty much lined up due north-south. So what we notice is when we tape our magnet to our piece of foam and we allowed it to float in a dish of water, it always turns to align itself in an approximate north-south direction. So the end of the magnet that points north is called the north seeking pole, which we shorten simply to the North Pole. So that's the North Pole of our magnet. It's the one that aligns towards the north. The end of a magnet that points south is called the South Pole. So now that we have names for the north and south pole of our magnets, let's look at what happens when we have two different magnets, and they each have, of course, a north and south pole. So what we're going to do in the first part was we're going to bring the north pole of one magnet near the north pole of another magnet. And then we're going to bring the north pole of one magnet near the south pole of another magnet and see what happens. So here is our experiment in this case. And we see that we've got two magnets. I've lined them up. It's the same magnet that we saw before. We knew which one was its northern end from the first experiment. And watch as I bring one magnet towards the other. As I bring it towards the other magnet with both north ends facing each other, they repel each other, and I can push the other magnet across this plastic board that I've set down here to have no interference. Now I'm going to turn the magnet around, and in this case we see I'm turning it and flipping it, and once I've flipped it, now we have both the north and the south poles are facing each other, and so now we have an attractive force and the magnets are attracted together. So let's see, if the north pole of one magnet is brought near the north pole of another magnet, what we saw was that they repel each other. Similarly, so we see what the image would look like right here, where they're repelling each other. Now, if similarly, if two south poles will also repel each other. However, the north pole of one magnet will exert an attractive force on the south pole of another magnet. And that's what we saw when the magnets clicked together. Now let's see what happens if we take a magnet and we bring it near a compass needle. So I'm going to take a magnet and bring it near our compass needle. So you saw that compass I had there, and we're going to take our magnet and bring it near that compass. So here we're going to pick up the magnet here and take it over towards our compass, and we'll see what happens with just one of those magnets. Here's our compass, and take it and when we bring our magnet near the compass needle, we're able to get that compass needle to turn just by having the magnet there. The magnet, one side of the magnet will push away the end and the other side is pulling the end, and we're able to get that compass needle to turn just by the presence of the magnet. So we see that the north pole of a bar magnet attracts one end of the compass needle and repels the other. So apparently the compass needle itself is a little bar magnet itself with a north pole and a south pole. All right, so now let's look at our fourth experiment. In our fourth experiment, we want to see what happens to a magnet if we cut it in half. So if I cut it in half right in the center, I should be cutting off the south end, the south pole and the north pole, and I should have just a piece of north pole and a piece of south pole. That's what we should do. It would seem logical. So let's see what happens when we do that. Here is our this is a magnet that I'm able to cut, which is why I chose this magnet. It's a very weak magnet. It's pretty thin, so it's a little hard to see, but let's see if we can see what's happening. And this is another magnet that we're gonna bring it next to. So here's the thin magnet. Bring it, and you can see, yeah, it does have a southern end to it where we're able to push on it, and then I can turn it, and at that point, it'll actually has the northern end where it's sticking to it, or vice versa. And now I'm going to take that magnet and cut it in half. So I've cut that magnet in two different pieces. And now when I take it to the magnet that's on the ground, I see that it still has, it's still a full magnet. It has its attractive side and its repulsive side. So what we see is that cutting a bar magnet in half produces two weaker but still complete magnets, each with a north pole and a south pole. And we can keep cutting it in as many pieces as we want, no matter how small the magnets are cut, even down to microscopic sizes. Each piece remains a complete magnet with two poles. Now, we've seen how magnets interact with each other. Now we want to see how magnets interact with other objects. So let's see what happens if we bring a magnet near some metallic objects. One object we'll use are paper clips, and the other one we're going to look at are pennies. All right, so here we have some paper clips and some pennies, and we're going to take I'm going to take a magnet right here and take it up first to the paper clips. So I bring it near the paper clips, and I take the bigger paper clip, and it jumps up. It can attract the paper clip, and now the bigger paper clip itself is now acting like a magnet, and it is picking up the other two smaller paper clips. So bringing a magnet near our paper clips allows that magnetic material the paper clip is made of to become magnetic itself. Now let's see what happens if we bring it near these copper pennies. One of them is a dull copper penny, doesn't have any attraction. Try to bring it by the bright copper penny, what's the problem? Nope, still no attraction. So copper pennies are not magnetic and have no attraction to a magnet. So what we see is that magnets can pick up some objects, such as paper clips, but not all objects. If an object is attracted to one end of a magnet, it will also be attracted to the other end. Most materials, including copper, a penny like we just saw, and aluminum, glass, plastic, they will experience no force from a magnet. There are some objects like paper clips and iron objects. Those are ferromagnetic and they will experience a force from a magnet. Moving on to experiment 6. In experiment 6, we're bringing a magnet near an electroscope. And we see that a magnet does not affect an electroscope at all when we bring it near an electroscope. A charged rod will exert a weak attractive force on both ends of a magnet. So like we saw with our charged rod when we were looking at our experiments discovering electricity, we saw that charged rods can exert attractive forces on objects. However, the attractive force that's exerted on a magnet is the same as what it would be if it were just a metal bar that wasn't a magnet. And so in this case, well, all we're doing is we're polarizing the magnet. So this is just a polarization force, like what we saw when we were looking at the charged rod when it was polarizing neutral objects. So other than the polarization forces, charges have no effects on magnets. So other than polarization forces, the only one, charges have no effects on magnets. So just a charge isn't going to affect a magnet. All right. Let's summarize and bring this all together. What do these experiments tell us? Well, first of all, magnetism is not the same as electricity. We saw that if we bring a magnet near an electroscope, there is no effect. So it is not the same as electricity. Well, a charged rod will not interact with a magnet in the same way. Magnetism is a long range force, just like electricity. We saw that we were able to push one magnet across the plastic table without even touching it. So there is a long range force for magnetism. All magnets have two poles called north and south. Two like poles exert repulsive forces on each other, and two opposite poles attract. The poles of a bar magnet can be identified by using it as a compass. So we were able to turn our little bar magnet into a compass by putting it on the piece of foam and floating it in the water. The north pole tends to rotate to point approximately north. Materials that are attracted to a magnet are called magnetic materials, like our paper clips. The most common magnetic material is iron, and other materials that are not attracted to magnets are non-magnetic, like our copper pennies. So those are our basic experiments to show us some basic properties of magnetism.